Good day, I'm Norman Wobbeker. We've been talking about the relationship between polynumbers and vexels, or vectors, and now we want to incorporate natural numbers, or particularly the Hindu-Arabic form of natural numbers, into this story. It turns out that fits very nicely. So we're going to have a kind of convergence of several seemingly different kinds of objects, all somehow captured by essentially the same mathematical configuration. So that configuration is that of a vexel. And a vexel was a multiset consisting of singletons. And a singleton was a list of just one natural number. So usually we write a vexel like this, where we can see the singletons quite clearly. But in fact, a singleton like this is actually, if you look at it strictly speaking, something that looks like this. Okay, so here's the bracket outside there, but inside this 2 is actually the M set of unit marks contained there. So there's a mark and another mark. That's actually what the natural number 2 officially is. So officially this vexel actually looks more like this. And it's useful to remember that it fundamentally has this almost very primitive aspect, just built up from our data structure point of view, from these essentially fundamental objects, these somethings, these unit somethings, or marks on the page. Now this notion of a vexel has an alternate formulation, or another way of representing it is in terms of a vector like this, where we record the multiplicities. We say that there's 2 zeros, and 1 1, and 3 2s, 0 4s, and 2 5s. And then when we look at it like this as a vector, well, that's really almost the same as what we formerly called a polynumber, and wrote like this with a little bracket up on top. And that polynumber had another representation in terms of powers of alpha, as 2 alpha to the 0 plus alpha plus 3 alpha squared plus 2 alpha to the 5th. So we have these various things which are all pretty well essentially the same thing. But I want us to think about the vexels as being primary, that it's really this thing here, this object here, which is the fundamental container, which is then being interpreted in a number of different ways. And in today's video we want to extend that interpretation in a different direction to give us Hindu-Arabic numbers or numerals. The big advantage in regarding the vexels as primary is that then the operations become particularly simple to state, and their properties become relatively obvious. So addition of vexels is really just M-set addition, because vexels are, after all, M-sets. That's what we do when we add vexels. And multiplication is the M-set extension of this fundamental multiplication at the level of singletons, where the singleton n times the singleton m is the singleton n plus m, where here is the ordinary addition of these two natural numbers. So for example, if we have this vexel here and this vexel here, then here is the sum and here is the product. I'll just remind you the product is obtained by taking all possible products between the elements of this one and the elements of this one. So this 0 times this 0 will be this 0. This 0 times this 2 is 2. This 1 times this 0 is 1. This 1 times 2 is 3. And similarly, we get another 1 and 3 over there. Now at the polynumber level, the same kind of thing would be written this way. This thing here would be the polynumber 1 plus 2 alpha, or maybe alpha 0 plus 2 alpha to the 1. And this thing here is just alpha to the 0 plus alpha squared. And then the corresponding multiplication is just the usual kind of polynomial multiplication. And it ends up being exactly the same thing as this one here. So this very simple multiplication of singletons really generates the polynomial arithmetic. All right, now we would like to add Hindu-Arabic arithmetic to the situation. And I remind you that our Hindu-Arabic numerals are thought of as independent of our natural numbers logically. There's a close connection, but we don't want to restrict our Hindu Arabic numbers just to be representations of our primitive natural numbers. If we did that, then we would only have numbers up to 10 to the 200 roughly, and we want to have a wider range of numbers. So our aim is to try to find a separate framework for Hindu Arabic numerals and have definitions and operations and proofs of the operations which are largely independent of the natural number system. And we're going to take our direction from the parallel that exists between arithmetic with Hindu Arabic numbers and arithmetic with Pali numbers, or now also vexils. And that's illustrated with these two examples. Here we have an addition of ordinary numbers. 302 plus 47 is 349. And correspondingly over here we have the Pali numbers 203 plus 74 equaling 943. Multiplication, if we have, say, 423 times 12, here's the familiar way of multiplying these numbers. 2 times 3 is 6, 2 times 2 is 4, 2 times 4 is 8, 1 times 3 is 3, 1 times 2 is 2, and 1 times 4 is 4. And then we have to add them appropriately, 6, 7, 10 with a carry, and 5. And note the parallel between that and multiplication of the corresponding Pali numbers down here. If we take 324, that Pali number, and 21, and we multiply them, we also have the similar kinds of operations occurring. So 3 times 2 is 6. And this 7 occurs from adding 3 times 1 and 2 times 2. The 10 occurs by adding 2 times 1 and 4 times 2. And the 4 is obtained by this 4 times 1. So exactly the same products that were happening over here. There were actually 6 products here, and there were also 6 products that were figuring, exactly the same 6 products. A slight difference is that over here we're not compelled to carry. Right? We don't mind having 10 in that spot. We're not obliged to change that 10 into a 0 and add 1 to this 4 to make it 5. So in the vexil world we would not do that. But over here in the Hindu Arabic world we do that. So there is a parallel, of course, but there's also a big difference having to do with the carrying aspect, which is related to the fact that each one of these positions only supports the digits from 0 to 9, and nothing bigger than that. While over here, we're quite happy to have numbers which are bigger than 10 in any spot. All right, so there's a parallel, but there's also differences, and we want to understand the relationship between these two things, and ultimately we're going to define this world in terms of this world. Let's remind ourselves about this subtle but important aspect of carrying in our ordinary arithmetic. Of course we know that it's based on having powers of 10. This 2 is 2 times 10 to the 0. Here we have 0 times 10 to the 1, and here we have 3 times 10 squared. And the crucial thing is that 10 ones equals 1 10. They're exchangeable, while 10 tens is the same as 100, and 10 hundreds equals 1,000, and so on. And that applies to each one of these positions, and it's kind of obvious because we have just powers of 10. All right, so it's using this exchange convention, really, this is underlying the fact that in the Hindu Arabic system we end up only having at most 9 of any quantity in any position. Right? We can jack that digit up to 9, but no further. And so we can think about this, if we like, going back to one of the earlier videos in the series, going back to primary school. We can think about having 17 $1 bills and 48 $10 bills. And what we're really allowed to do is to exchange, to convert $10 bills into $100 bills, or $10 bills into $1 bills, and so on. But as long as we obey the right exchange rules, which are given here. So we can rewrite this as 7 times $1 plus 9 times $10. So we have 8 times $10 over here, and there's another 1 times $10 because there's 10 ones here that can be converted to a single 10. Altogether 9 tens. And hundreds, well, there's actually 40 tens that we haven't taken care of over here, and those 40 tens can be converted to 4 hundreds. This basic idea of converting some sort of general combination of 1s and 10s and so on into a particular combination where all the coefficients happen to be less than 10. If any one of them were bigger than 10, it means that we can make some further exchange and create more of a higher unit and lower the actual coefficient so it's in the range from 0 to 9. All right, so this is basic exchange aspect that we want to get a hold of. So we're in the position now of having to define, or try to define, what the Hindu Arabic numerals are. In other words, we need to give definitions. Even though, of course, we all have an intuitive understanding of what these things are. And of course, it comes down to the fact that we have 10 fingers on our hands. That's the ultimate reason why the powers of 10 are important. But from a mathematical point of view, we could readily ask, well, why 10? If we're going to create this system, this sort of official mathematical system, does it make sense to base it on 10? Won't that make it rather arbitrary? How about 16, or 5, or 20, or 60, or 2, in fact? So what we are kind of obliged to do, if we are going to proceed formally in this direction, is to distance ourselves a little bit from the tenfold aspect of our familiar system and think a little bit more generally. Okay? And we're going to do that by actually having a look at this simpler version first. So the essential idea can be captured already here in base 2. And it makes sense to treat that sort of separately because it's an important kind of stepping stone. So now let's have a look at base 2 vexils. We're going to take our ordinary theory of vexils and we're going to adjust it in a small way. We're going to add some new rules, and then that will give us these somewhat new kinds of objects, base 2 vexils. And the new rules that we're going to add can be described this way. That if we have a singleton 0 together with a singleton 0 together, they can be exchanged by a singleton 1. It's the kind of base 2 equivalent of 10 $1 bills equals 1 $10 bill. But it's at the level of singletons. We're just saying how we can replace one configuration with another configuration, typically in a multi-set. And similarly, if we have a singleton 1 together with a singleton 1, we can trade them in for a single singleton 2. And we can trade two singleton 2s in for a single singleton 3, and so on. So this can be represented more efficiently by the single rule, this one here, that a singleton n together with a singleton n equals a singleton n plus 1. Now this is not meant to be interpreted in terms of multiplication. Okay, we are not defining a multiplication here. We're rather making a statement about, in a multiset, if we have two of these things in a multiset, we can replace them with a single n plus 1 singleton. So let me illustrate this with an example. So here is a vexil. It's a traditional ordinary vexil, but now we're subjecting it to these rules, or essentially to this single rule, if you like. And that means that these two zeros here can be replaced by the singleton 1. And these two 2s can be replaced with the singleton 3. So we get a 3, we get a 1 from here, a 2, and these two 5s can be replaced with a singleton 6. But then we can do the same kind of thing because now we see we have two singleton 1s. They can be exchanged for a singleton 2. And then in the next step we see we have these two singleton 2s which can be replaced with the singleton 3. And now we're still able to do one more thing because the two singleton 3s can be replaced with a singleton 4. So in this way we have transformed the original vexil into another vexil, and we regard all of these vexils as being equal in this base 2 framework. So we're defining a new kind of equality between vexils, which rests on the exchange encoded in this equation here. So to summarize, two vexels are, say, base 2 equal precisely when we can get from one to the other by repeated application of this basic exchange condition. Now we can write this kind of exchange story also at the level of vectors or polynumbers. Let's illustrate that. So here is a vexel written as a polynumber now. 213002. All right, so what we're allowed to do is we can take these two, these are basically two 0 singletons that are represented here, and replace them with a single 1 singleton. So they disappear, but the number of 1 singletons now has increased by 1. And similarly down here we have two of these. We could replace them with a single one further down. Okay, now from here we could replace these two at level 1 with another one of level 2. So there'd be now 4 at level 2. And then at this next stage we take these 4 and exchange them in for 2 of the higher ones. In other words, 2 level 3 fellows. And then at the last stage we interchange those 2 level 3s for a level 4. So it's the same kind of story, but it's just in the context of these polynumbers. And what we get at the end is alpha to the 4th plus alpha to the 6th, if we want to represent it as a polynumber. And I think we can see that repeated application will mean that all coefficients are either 0 or 1. Because whenever we have a coefficient which is bigger than 1, that means we can take 2 of them, combine them, and replace them with something that's 1 higher up, and then the number of coefficients will have dropped by 2. So if we keep doing that, then eventually all of the coefficients are either 0 or 1, just like in here. So it makes sense now to introduce a new type, let's say vex2, representing a new type of object which consists of vexels together with this base 2 equality that we've been talking about. So for example, 512, you can check that's the same as 132, which is also the same as 1111. And this is now an equality in vex2. Alright, so now there's an interesting exercise for you to think about. We've defined these new type of objects, these base 2 vexels, and we want to now appreciate that addition and multiplication of vexels are actually well defined in here. Okay. That means that, let's say we consider a particular equation, 512 plus 401. So if we do addition, that would be 9 and 1 and 3. Okay, we recognize this as something that's familiar. Now over here we have different versions. So 512 is 1111. I've replaced this one with another version which is equal to it. So this is another vexel, but it's actually the same vexel as that one in vex2. And we've replaced this one here with 0001. That's 1, 2, 4, 8. That's like 8. This one is like 4 plus 4. It's also 8. So these are really the same. And in other words, we could go from here to here by a number of exchanges. We could replace this 4 with 0, 2, and then we replace this 2 with 0, 2, and then we replace this 2 with 0, 1. Now, if we take these things here and we add them using ordinary vexel addition, we get a 1, 1, 1, 2, which converts to 1, 1, 1, 0, 1. And the claim is that these two things that we end up getting here are actually equal under the exchange conditions. So if the ingredients are equal with respect to the exchange conditions, then the final results will also be equal with respect to the exchange conditions. And that's true not just of addition, but also of multiplication. So please have a think about why that is, and in our next video we're going to talk a little bit more about this base 2 arithmetic and why it works, and also give you maybe a geometrical appreciation for what's going on here. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.